Hi everyone. This section is an intro to differential equations, which we actually touched on a little bit way back in the beginning of the quarter, but you can spend like multiple quarters talking about differential equations, so I want to get into it just a little bit more. I think the beginnings of this are actually kind of fun. There's a little bit of vocab and graphing stuff to get used to, but otherwise by the time we get to 4.3, the work of it is just practicing your integration technique, so I love to just get to chat about this a little at the end of the quarter. So I think I want to first just remind you about the 1.1 version of this and then introduce a little bit more of the vocabulary. I maybe used it then, but I don't know how much I really got into it. So a differential equation is an equation that tells us about the rate of change of an unknown function. So when we think about solving equations in algebra, we're trying to find the value of x, for example. When we're trying to solve a differential equation, we're trying to find a function for which the statement is true. So in 1.1, we got fairly straightforward statements like, oh, hold on, my pen's not set. It is set. Hold on. Unscrew my pen. So like dr dp is equal to 3 sine p. So that's telling me that function r is the function whose derivative is 3 sine p. And we can talk about finding the general solution or a specific solution, particular solution. And then there's even this initial value vocab that doesn't really add a lot, but is used. So let's see if this is working out. It is. Okay. I am looking for the function whose derivative is 3 sine p, and I would say that that function better involve a cosine p, and it better involve the p, but the derivative of cosine is minus sine, so I'm going to throw in that extra negative to make that work out. And I'm looking for the general solution, so this should be like the general antiderivative. The general solution is that the functions that satisfy that differential equation will all have the form -3 cosine p plus c. So if we want just one solution, one function, instead of the whole family, that's when we talk about the particular solution. So the only difference here would be you have to be given information that helps you figure out which of those curves you're looking for. And then we just use it as we did before. This says if we plug in pi over 2 4p, 4p, we should get 4. Oh my goodness, I'm having a hard time talking and writing at the same time. Cosine of pi over 2 is 0. So this is all going to be 0, which means that the value of c is 4. So the solution to this differential equation will be r of p is equal to -3 cosine p plus 4. And then last but not least, sometimes the condition that you're given is a special one, in that it is an initial condition, the Y-intercept basically. So you're told the initial condition on the situation, and it's just like finding the particular solution. The only difference is that that is a Y-intercept. So now I would say I've got my -3 cosine p plus c. And when I plug in 0, cosine of 0 is 1. So I get -3 times 1 plus c, and that should equal -1. So in this case, my c is going to equal 2, and the solution to the initial value problem is r of p is equal to -3 cosine p plus 2. Okay. So that's kind of our basic little bit of vocabulary, but these really are kind of simple examples of differential equations, even for what we're going to get into. So I want to jump a little bit and think about what something like this is telling me. So this is now telling me not directly what the derivative is, but that the derivative of the function is the function. So that's kind of an interesting one. And I think if you stop and think about it a little bit, you can probably even come up with some possible answers. I could guess that r of p equals e to the p would work. That's not the only thing that would work, but avoid things like, sometimes people want to say, well, it's e to the p plus c. That doesn't actually work because the derivative of that, oh my goodness, my pen is being terrible today, is just e to the p, which is not the function we started with. So actually what we want to be a little more general would be c e to the p. In that case, whenever we take the derivative, we will still get back to what we started with. So this is a little bit more interesting differential equation for us. We have had to think like this before in Calc 1. This might seem brand new, but think about implicit differentiation. So if I have something like r times p equals p squared plus 1, and I want to find dr dp, we would take the derivative of both sides with respect to p. So we would say d dp of rp is equal to d dp of p squared plus 1. And whenever we hit an r, we just want to remember that that's a representation of our unknown function. So now we have dr dp. Okay, so let's see, this is a product rule. I should be clear on what we're doing. Times p plus r times dp dp, which is 1, is equal to 2p, and you could think of chaining out a dp dp, but again, that's 1, plus 0. So this could be considered a differential equation. This could be considered a differential equation. We can even keep going. If we were actually going to finish this problem, we would move the r over to the other side and say dr dp is equal to 2p minus r over p. That could be considered a differential equation. So this one says the derivative of our mystery function r is going to equal 2p minus the original function divided by the original function. Which I certainly, just looking at that, couldn't tell you what the answer was, but since we reverse engineered this, we could say, well, if we want to figure out what function r is, we could just solve for r. And this function, p squared plus 1 over p, would be the solution to that differential equation, or we could simplify it, p squared over p plus 1 over p. That function would satisfy the differential equation 2 times p minus my function divided by p is equal to the derivative of my function. Okay, so all very messy, but this is the same kind of thinking where we have a variable floating around that actually represents a function and not just our usual independent variable business. Okay, so this is kind of the beginnings of differential equations. I've got a few more examples for you to play around with, but again, this section's really just about getting used to how differential equations look and a little bit of vocab and what it means to be a solution to a differential equation. Okay, thanks for watching.